All right, we are getting into an explanation or a unit that is dealing entirely with what we call quadratic equations. Okay, now quadratic equations, they're not all that difficult, okay, but they are different. Okay, but a quadratic equation, all it is an equation that generates a graph, just like any other equation. It generates a graph. We get points from our equations, we get points into our graphs, we connect the dots in our graphs, and we end up with a graph of something. The difference is the vast majority of everything that we've worked with so far, straight lines. Okay, straight lines. Quadratic equation is going to bend. Okay, and we've seen this. We've looked at it a little bit already this year. Do you remember what we call those graphs that bend one time? It's a quadratic equation, but the graph itself has a name. You remember what the name was? Yeah, P word, parabola. Okay, graphs of parabola. Good. Okay, so what we're going to do is we're going to take a look at this. We're going to go through these questions together. Want to kind of help you get your feet wet, get you used to what parabolas are going to do, what their little properties are, how they're going to look, stuff like that. So please follow along and take notes on your paper as we come up to answers up here. Okay, so first off, Greg is preparing to dive off a 4-meter diving board. His distance above the water level is 4 meters. As he jumps, his distance from the water surface increases. His distance back from the his distance from the water surface reaches a maximum height, and he no longer goes upward, but begins to fall back down towards the water. Now his distance from the water decreases. If you were to graph the diver's distance above the water over time, what would the graph look like? How is the graph the same or different than ones you've already created? Blah, blah, blah. Okay, now let's think about this little situation that they're talking about here. Okay, you got this guy and he's 4 meters up on a diving board. Okay, now typically, unless you're like 3, you don't just stand on a diving board and then just lean forward and fall off. Okay, that's how people go off the first time, but typically they learn to run, jump, spring upwards, right? Okay, so let's think about what this diver's height does. Okay, when he's on the diving board, he's standing there. Okay, when he jumps, what happens to his height initially? Does he jump downward? Does he jump sideways? Jump upward? Typically, they try to jump upwards, right? Okay, you run to the end, you spring off the board, push off with your knees, okay, and you jump upward. So initially, what we would expect to see a graph do is he's standing on a 4-meter tall diving board. We would expect his height to go upward some amount. Okay, now let's think about that going upward part. When he takes off from the board, okay, does he take off quickly? Does he take off slowly? What would you expect his height to do? We said it's going to go upward, but is it going to go up kind of in a big chunk right off the bat? Okay. Well, how about this? As he continues to go upward, what will happen to his height? I mean, he'll still go up. Will he continue to go upward at the same speed? He gets faster, so he takes off from the board and he rockets off toward God, gets faster and faster. Okay, gets slower, right? Takes off and he's going to go upward. Now, gravity's working on him all the time, right? Okay, constantly being pulled. Okay, but as he jumps and exerts that force, okay, gravity's working on him, but it's having to work on the full force of his jump. But as he has finished the jump, he can no longer push anymore. Okay, so whatever he's got going upward, that's all he's got. But gravity continues to work against him, right? So as he takes off, his height may be increasing pretty quickly, but then as gravity continues to work on him, it's going to slow him down until eventually he reaches a point where he is no longer going upward, right? His curve or his height is going to reach a peak and it's going to say, okay, dude, you're not going any further than you went right here. Then what happens? Yeah, gravity is continuing to pull on him all the time when he's going upward, when he's at the peak of his height, and when he begins to come downward. Gravity continues to pull. Now, when he gets to that peak, does he take off from that peak and just go like he goes up and then just goes, shoom, I mean, straight down like a rocket ship? No, it's a gradual increase, right? Okay, gravity begins to pull on him and it starts to pull him back down. But what happens as his momentum gets going down? Gravity's still pulling, but since he's already moving in a downward direction, the gravity keeps pulling with the same force, but he ends up going faster and faster and faster as more time goes by because the gravity continues to pull on him. Okay, so what we would expect as he leaves the diving board, his curve is going to shoot up. fairly quickly. Okay, but then it's going to slow down as gravity does its work. It will reach a peak or a spot where it's going to turn and go the other direction, and then it will gradually start heading back the other direction, and it will increase as more time goes by. Okay. Now what we have here is we have a chart that says it goes by 0.2 seconds, and for each 2/10 of a second that goes by, we have a distance above the water that we're given. And you can see he starts off at 4 meters. There reaches a point where his height is maximum. Okay, and his height begins to start to decrease again. Okay, that's him at the peak of his height, and the height continues to decrease. Oh, sorry, the height continues to decrease over here on the right side until ultimately he has zero height, and then he even has negative height. Well, what the heck do you think that means, negative height? He's in the water, right? I mean, if he was fool enough to go off the side of the diving board, well, when he reached the concrete right there, he would go splat and he wouldn't go any further. Okay, but since it's in the water, now he is below the surface of the water, so it is possible we end up with negative heights because he's now underneath the water. Okay, let's see if we can answer some of the questions that are going to follow here based on this chart. Okay, first one says, create a scatter plot of the data in the table. Graph time along the x-axis and distance along the y-axis. Okay, time along the x-axis. That's what they said. Do we need them to tell us this? The time goes on the x-axis. Do we need them to tell us this? Will they ever tell us that time goes on the y-axis? Everybody in here needs to know the answer to this question. Okay. Okay, now what I need to say now is everybody in here needs to not just be tuning me out and just sitting out there and go, wait, what? I wasn't listening. Okay. They said that time goes on the x-axis. Is that news to us? No, it's not. Okay? Because if time is ever a part of the problem, it always goes on the x-axis. Exactly, and we'll get to that here in just a second. Okay? So label your x-axis. I can't get underneath my graph there because I don't have any space on my screen, but label underneath your graph is time. They also announced for us that distance would be on the y-axis, which was kind of the dumb thing of all time to say because we didn't have anywhere else to put it anyhow. Okay, so label the vertical side of your graph as distance. Okay. Now it says to create a scatter plot of the data on the table below. And it also on number 2, I think number 2 should have been part of number 1, but they chose to separate it for some reason. Label the area on the graph above water, water surface, and below water. Okay, well, that has to do with the height. Okay, how far he is above or below the surface of the water. So what I think we'd probably be best served doing is coming across about the center of the graph and saying that that is the water surface. Okay, and it says to also label the information as above the water and below the water. And it's kind of important to have that information in the graph because if they want us to create a scatter plot, well, we'd probably better know where 0 is at, where the water surface is at. Okay, so that's what I'm going to do next. I'm going to say, all right, water surface is 0 meters. Okay, and let's see. Looks like we got to go fairly high up and fairly far down. So I'm going to let each grid line going up the y-axis just be 1 meter. So I'm going to go 1, 2, 3, 4, 5 meters, 6, 7, 8, 9, 10 meters. Down 1, 2, 3, 4, 5 meters, and down 1, 2, 3, 4, 5 more. Now look, if you manage to get that water surface line right in the middle of your graph, it works out pretty nicely. You get up to positive 10 and down to negative 10. And we also need to figure out how much each grid line we're going to allow for time. Okay, well, the time is moving by 2/10 of a second for each of the lines in the chart. Okay, so that may be the easiest thing to do. Let each grid line be 2/10 of a second. So you'll start off right there. I know you can't really see it on mine, but start off at 0. 2/10, 4/10, 6/10, 8/10, and 1 second right there. 2, 4, 6, 8. 2 seconds, 2, 4, 6, 8. 3 seconds. Okay. Again, I apologize. I can't get much better underneath my graph there. Okay, and it did tell us to create a scatter plot. So we're going to transfer the information real quickly out of this chart into the graph. Okay, now since every grid line was 2/10 of a second and the chart is moving by 2/10 of a second, then all we really need to do is travel along the y-axis and figure out how to label him. At 0 seconds, he is 4 meters high. Okay, after 0.2 seconds, he's up to 5.4. Next one would be 6.4, 7.0, 7.2, 7.0, 6.4, 5.4, 4.0 again, 2.2, and then impact with the water surface there, down 2.6, 5.6, and 9.0. Not real sure what happens to him after 2.6 seconds that he's down under the water 9 meters, but they don't ever give us anything beyond that. Okay, so what you should have gotten if you graphed your points well and then done a better job of connecting the dots than I did, okay, you should have a nice smooth parabola. Okay. Okay, keep working on that. If you're not finished, we're going to look at the next question. Think about the situation. Now, Joabel's already answered this question for us, but what is the independent variable? Okay, well, let's just do this first and foremost. Which axis is always going to get the independent variable? Exactly, the x-axis always gets the independent variable. Okay, it doesn't matter what the independent variable represents. Okay, it'll always be on the x-axis. Now, don't get me wrong when I say it doesn't matter what the x-axis represents, because it does. Okay, and we already said, repeat it for everybody, Joabel, what did you say was going to be independent? Time. Okay, time always gets the independent axis. It always gets the x-axis if it's part of the problem. Okay, now typically stuff that goes on the x-axis, if it is present in the problem, this is the stuff that we have no control over. Okay, which is probably most importantly in a graph is typically time. Okay, and I always use the same example. I can go back there, I can snatch that clock off the wall, I can smash it on the ground. Did I just stop time? Of course not. It's going to continue on no matter what. Okay. Which brings us to a discussion of the dependent variable. Now, the dependent variable, quite obviously, is always going to get the y-axis. Okay, and in this case, what is the independent or the dependent variable? It's distance or height or however you want to term it in this particular case. Height, distance, it's the same. Okay, and the way this relationship exists, and we all need to know this relationship, is it's really quite simple. Okay, the stuff that's on the y-axis depends upon where you're at on the x-axis. His height jumping off the diving board depends on how much time has gone by since he jumped. Okay, the height depends on the amount of time that goes by. You can't say the amount of time that has gone by depends on how far up in the air he's at. No, I mean, time isn't going to wait for him to do whatever it is he's going to do. Time's going to continue moving. His height will depend upon how much time has gone by. That's why we call the x-axis independent. It controls the entire problem. Everything else depends on what the x-axis is doing. Okay. All right, now here on number 4, what is the domain and range for the problem situation? Okay, well, a couple pieces of vocabulary there. And again, everybody's responsible for these two terms, which we've seen 100 times, but we still manage to get them confused. Okay, domain and range. Okay, generally speaking, what are you supposed to think of when they throw the word domain at us? I'm sorry, say again? No, I don't think so. It's the x-axis, okay? Domain is a representation of what's going on with the x values, okay? Which means range is a representation for what's going on with the y values, okay? Now, I always give people the same thing to try to remember this, and I guess I'll just keep on giving it to us, hopefully until we figure it out, okay? Domain and range, D and R. Okay, what comes first when you're thinking alphabetically, D or R? Obviously D does. Okay, now x-axis and y-axis. What comes first when you're thinking alphabetically? The x does. Okay, D comes before R, x comes before y. D before R, x before y. The D and the x go together. Domain is x's. Okay. On the other hand, R comes second in the alphabet, Y comes second in the alphabet. Range and y-axis belong with each other. If you see a domain or range question on a tax or a star or any other test ever, okay, chances are you will see two answer choices, okay, that will talk about x's and two answer choices that will talk about y, okay, but the question will only ask about one or the other. It'll either say domain or it'll say range, but there'll be two x's and two y's in the answer choices. The only difference between getting the right answer and the wrong answer is knowing that domain is x, range is y. They do this to us every single year. Okay, we need to know the difference between domain and range. Okay, so what is the domain and range for the problem situation? Okay, well, let's have a look back here. Okay, let's think about domain. Okay, how far or where does the graph exist along the x-axis? Okay. Well, when we're looking along the x-axis, when the graph starts off right there at 0 seconds, is there a graph going on? Yeah, it's up there, right? I mean, it doesn't have to be on the x-axis. It's just as you look along the x-axis. And as you start off at 0.0 seconds, is there a graph that's going on at 0.0 seconds? There is. That means that 0.0 seconds is part of the domain. Okay? There is an x value participating in this graph at 0.0. And as you continue to move along the x-axis through all these fractions of seconds, does the graph continue along with it? It does. As you move along the x-axis, the graph continues along. And as long as the graph continues along as you move along, then that is part of the domain. Well, where do we finally run out of domain at? Right there. After we get there, the graph vanishes. Okay, well, where is that? Well, it's a little hard to see in my graph, especially since my board can't draw where I'm trying to get it to draw. But we can look in the chart and go, you know what, where do we finally run out of x-axis information? Well, we run out at 2.6 seconds. Okay, so the graph begins in the domain on the x-axis at 0.0 seconds, and it doesn't quit until it gets out to 2.6 seconds. That's the answer to the question. What is the domain and range for the problem situation? Well, the domain is, it's an x value, and x is between which two numbers? It's between 0.0 and 2.6. 0.0 is smaller than or equal to the amount of time, and the amount of time is smaller than or equal to 2.6. Another way people like to think of it is x is between 0.0 seconds and 2.6 seconds. Okay, so there's the answer to that. We also have to answer for the range. Okay, well, the answer for range is, well, as I travel along the y-axis, where does the graph exist? Well, where does the graph first exist on the y-axis when you're coming up? Okay, it kind of comes into being right there when he is -9 meters down. He's at 9 meters under the water. Okay, so that's where the y-axis kind of first comes into play. Okay, so the question now is, as we continue moving along the y-axis, is there a graph coming with it? And there is. Okay, so all these values coming up are in the range. Okay, where do you finally run out of information on the range? Somewhere in there. Okay, somewhere in there. When he jumps off the board, he reaches the height, gravity's got him, he's no longer heading upwards, now he's heading back down. That very top piece of information, which is sitting right there in your chart, is where the range finally gives up. Okay, so our range is going to begin down at -9, and it's going to continue all the way up to 7.2. So range, this time y values are between, where did it begin? -9.0. Where did we finally run out? +7.2. Now, another question that's in this question, number 4 here, is it continuous or discrete? This is a term we've talked about before. So if you're new to class this semester, you may have forgotten this one somewhere along the way. Continuous or discrete. Does anybody remember the difference between those two words? Yeah. Yeah, I think continuous is a pretty easy word to understand because it kind of means the same thing to the graph that it means to us in the English language. Okay, continuous means it continues. It's not broken. It goes on kind of not necessarily forever, but it goes on uninterrupted. How's that? Okay, continuous means it goes on uninterrupted. Well, what do you think about this graph? Is it uninterrupted? Does it have a big gap in it anywhere? It seems like from the beginning of the problem to the end of the problem, the curve is nice and smooth. Nothing happens along the way. It's not like he jumped up into the air and a helicopter flew by and he splatted into the side of the helicopter and it carried him for a few seconds and then dropped him. Okay, the event that was happening happened continuously. Okay, a discrete graph would be something happens in the middle of the problem. Like maybe he jumps off the diving board, his height goes up, and then on the way down, maybe he hits the diving board, which of course slows him down or stops him, and then maybe he falls off the board or bounces off of it or whatever, and now he's heading back down again. That would be a discrete graph because something interrupted the way that the thing was happening. So is this graph continuous or discrete? It is continuous. Okay, this happened without interruption. There's no breaks in the data. Okay, if the data is continuous, draw a smooth curve through the points on the scatter plot. Well, I'm sorry, we already did that. We got a nice smooth curve going through our graph, so that's already taken care of. If the data is discrete, draw a broken curve through the points in the scatter plot. Well, it wasn't broken because it's not discrete. Okay, nice and smooth. All right, now let's get to number 5. This actually is some of the more important information when it comes down to new types of equations and new types of graphs. What patterns do you observe in the graphs? Well, take a second, glance at this curve, okay, or this graph, whatever you want to call it, and let's see if we can make any statements about it. Okay. Anybody notice anything about it they'd like to share with us? Because if you can notice it, it's probably a pattern, something we can all look for. Anybody see anything? Okay. Okay. What Julian's saying is that kind of like on either side of his maximum height, okay, that the increase or the decrease, however you want to look at it, is consistent on both sides. So it may decrease by some amount on one side, but it decreases by the same amount on the other side, and it does the same on both sides. And he's absolutely right. Does anybody know what that's called? Okay, when something's like you could actually put a line right down through the middle of something and it would make it the same on either side of the line. That's got a particular name. Symmetry, exactly. Okay, parabolas, which are the result of quadratic equations, they are symmetric. They have symmetry. Now, does anybody remember what type of symmetry that's called when you can put a line through it and it's the same on both sides? Because there's different types of symmetry. Anybody remember what that kind's called? Okay? If you don't remember, it's called reflectional symmetry. Okay, and if you hopefully might remember that through some discussions in junior high at some point in time, but if you don't worry, you'll get a good look at that when you get into geometry. Okay, but reflectional symmetry. Now, is it necessary for you to identify it as reflectional symmetry? It's kind of important. Okay, because there's other types of symmetry too. There's also what we call rotational symmetry. Okay, anybody heard of rotational symmetry before? Think about if you started off with a square. If you started off with a square and rotated it 90 degrees, would it look like it did before you rotated it? It doesn't? If you took a whole square, I mean, obviously I can't hold up a whole square with just my fingers, but if you rotated it 90 degrees and stopped, would you be able to tell the difference between where the square was before and where it is after the rotation? It would look exactly the same. You know, kind of like a round doorknob. You can sit there and you can spin it, and as long as it doesn't have a keyhole or anything like that, it looks exactly like it did before you spun it. That's rotational symmetry. Okay. We also have translational symmetry. Okay, if you think about the pattern like in a brick wall or something like that, could you draw a picture exactly of the brick wall with all the different little vertical lines and horizontal lines, and then take the picture and slide it over to a different place on the wall and it would look pretty much exactly like it did before you moved it? Yeah, that's called translational symmetry. Okay, so it does have reflectional symmetry. Now, if something has reflectional symmetry, like a parabola does, okay, then this guy right there is what we call a line of symmetry. And what people tend to think of a line of symmetry like is a mirror. Okay, when one side of the graph looks into the mirror, what is it going to see? It's going to see itself, okay, on the other side of the mirror. Okay, well, that's the way that these things are going to look. Well, you may be looking at it going, now, wait a minute, okay, when this side of the graph, when the right side of this graph looks into the line of symmetry, does it see itself out here? Well, in this particular instance, it doesn't, does it? Okay, because as we get to the edge, the left edge of the graph, we don't have any more graph. But we've got to remember, the reason there's no left side of the graph is because that's just the problem that they brought to us. But if we were to have an equation and punch it into a calculator or graph it or whatever, we would end up with the other side of that parabola. It would be completely symmetrical on either side of the line of symmetry. Okay, so it just happened to be the problem that kind of blocked off this part of the parabola that we couldn't see. But that doesn't mean it doesn't exist. Okay, so what patterns do you notice, observe about the graphs? Okay, reflectional symmetry. Now, Julian was talking about something else a moment ago. Okay, he's talking about the increases and the decreases on the y-axis. Notice anything about them? It's the same on either side, obviously, because of the whole reflectional symmetry thing. Okay, but is there anything else you notice? What happens to the step sizes as you get closer and closer to the line of symmetry? Yeah, the steps get smaller, don't they? Okay, the points start packing in together, and that is a property, okay, that's a characteristic, something you're going to notice about all parabolas, whether talking about a diver on a diving board or just any other equation that's going to graph quadratically, okay, what you're going to notice is that the steps, if you want to call them that, okay, probably about 100 different ways you could word it, but the steps get closer as you get closer or you approach the line of symmetry. I'm going to abbreviate it, line of symmetry, LOS. The steps get closer as you approach the line of symmetry. And that's what parabolas do. When they leave their line of symmetry, if you think about that diver, like when he's at his peak, gravity doesn't just snatch him out of the air and plummet him to earth at breakneck speed. It pulls on him and pulls on him. It gets him started, and the further he moves, the faster he gets. And the more time that goes by, the faster he gets. The parabolas work exactly the same way. The further they get away from that midline, that line of symmetry, what they're doing, they're going to do it fairly gradually, but as they get further away, it's like they build momentum. They gain speed, and then when it comes down to it, they're in a big hurry. Okay. Number 6 here is the function increasing or decreasing, and over which intervals. Okay. Well, we've talked about these two words, and everybody needs to know them. Okay, and these are not real rocket science. What are they asking for? What are they asking about when they ask us if a function is increasing or decreasing? Well, what about it getting bigger or smaller? Yeah, it's really this simple. Okay, the question would be, okay, whether the graph is simply going upward or whether the graph is simply going downward. That's what increasing or decreasing means. And while that sounds like kind of a Mickey Mouse thing to talk about, like, man, they could train any kindergartner to figure out the difference between increasing and decreasing, actually fairly important topic of discussion on some of the bigger level graphs. Okay, so you'll hear increasing and decreasing in algebra 1. You'll also work with it in algebra 2, and if you continue on into pre-cal and calculus, well, the idea of whether something is increasing or decreasing over a given time period is very important to the graph. Okay, so is it increasing or decreasing? Well, that's kind of a weirdly worded question. Is it increasing or decreasing? Yeah, it is both. It is increasing and it's decreasing. Okay, but anyway, so yes, it is, and over which intervals? Well, I don't know. Let's take a look. Okay, we're going to have an increasing interval. We're going to have a decreasing interval. Okay, let's see what interval it is increasing and what interval it is decreasing. Okay, well, pretty obviously, guys, increasing simply means the graph is going upward. So obviously, we're talking about these points that are climbing higher in the graph. Okay, so it is increasing on that interval. Now, this is a little bit different. Of course, we can see the values. What are the values? 0.0, and that line of symmetry is at 0.8 on the x-axis. Okay, so it's at 0.8 on the x-axis. So our interval on increasing is 0.0 on the x-axis up to 0.8. Now, I'm going to use different inequalities than I used on domain and range. Domain, it was okay for us to include the endpoints, which is how come I put the little equal signs on there. Okay, 0.0 was part of the domain. I wanted it to be included, so I put less than or equal to. 2.6 was part of the domain. I wanted it to be included, so that's why I put the less than or equal to. Same thing on range, less than or equal to, less than or equal to. Now, when you start thinking about intervals, intervals is like a boundary. Okay, it's like saying, hey, we are inside of the left-hand wall of the room and the right-hand wall of the room. Okay, so we are in the space between. Are we part of the left-hand wall or part of the right-hand wall? No, we are in between. Okay, that's the way these increasing and decreasing are going to work. They don't get the equals part of that inequality simply because at 0.0, the graph is not doing anything. It's just sitting there. At 0.8, the graph is not doing anything. It's just sitting there. So we really don't want to include 0.0 and include 0.8, but in between 0.0 and 0.8, it is increasing. Okay, let's look at where it's decreasing at. Well, the exact same theory and values. We've got all these points that are tumbling down. Okay, those are all decreasing because they're falling downward in the graph. And obviously it begins at, once again, 0.8. Okay, that's the edge of where it starts to decrease. And it doesn't quit decreasing until we run out of values, which is 2.6. Okay, so we got 0.8. Okay, on the x-axis. We've also got, what did I say the value was? 2.6. And once again, at 0.8, nothing is happening. At 2.8, nothing is happening. But in between 0.8 and 2.6, that's where we have the decreasing part of the graph. Okay. What else have we got? As time increases by 0.2 seconds. Okay, that's what our chart is doing. That's what our graph is doing. By how much does the distance change? Okay, well, I think that's a little bit of a loaded question. We're going to see why here in just a second. Does the distance change by the same amount over each interval? Well, have a look at the graph. The question is asking, by each 0.2 seconds, that's by each grid line that we come across when we're going across the x-axis, is the graph changing by the exact same y value each time. So as you move over 1 on the x-axis, and then you move wherever on the y-axis, that movement on the y-axis is the same amount each time. Okay. Well, the answer is really a pretty simple an answer. Is this a straight line? No. Does this have a slope like rise over run? Could I go rise over run? Go, I'm going to rise and run, rise and run, rise and run, rise and run. I'm going to get this graph? No, not even close, right? I mean, so this is kind of the dumb question of the day. Does the distance change by the same amount over each time interval? No, not even close, because if it did, you'd end up with a straight line going one way or a straight line going the other way, and obviously it does not do either of those. Okay, because if it increased consistently, we'd end up with a straight line. We didn't end up with a straight line. We ended up with a parabola. Okay, so that's kind of a duh question there. And then let's look at number 9. Okay, remember that a function pairs each independent value with exactly one dependent value. Is the relationship in this situation a function? Why or why not? Okay. Well, once upon a time, we defined what a function was, but it's probably been far enough into the past that anybody that did know it then has probably forgotten it. So what I want is I want everybody to write down a definition here. Okay. This is one of those everybody's responsible for this. We're going to face questions that are going to talk about functions at the end of the year, so we better know what it is when they say it. Okay. And a function's one of those that's got a big, long, complicated paragraph definition, but let me boil it down to you. A graph is going to be a function if every x value if every x value has only one y value to go with it. If every x value only has one y value to go with it. And while you're copying that down, I'll give you a little visual so you can kind of comprehend what it is that just said. For a graph, if we want a function, then we will never get a graph that does something like this. Now, what is it that makes this not a function? Well, the rule says for every x value, that means we can come anywhere we want on the x-axis. And at that location, you can look up from there or down from there, and you can find a y. That's okay. But if at that same location, you can find another y, that's a no-no. Okay? Functions will never do this. Having one y is okay. Having two y's is not okay. So when they say function, it doesn't matter if they're talking about a chart. It doesn't matter if they're talking about a graph. It doesn't matter if they're talking about a mapping, which is something else we're going to be seeing again this unit. It doesn't matter what they're talking about, an equation, a set of points. If you can look into the problem, and if for one x value anywhere you can find two y's that go along with it, that is not a function, and it's not going to work. Okay? So each function pairs each independent value. Those are the x's with exactly one dependent value. Those are the y's. Is this relationship in this situation a function? Well, let's have a look. Okay, I've written all over our graph, but let's look. Can you find anywhere in the picture, anywhere in the graph, where a single x value has two different y's to go with it? Okay, let's look. So if you started off here at 0, like somebody just said, okay, are there two different y's that go along with it? There's one. Do you find another? I don't see one. Okay, there's nothing stacked that way. Okay, just one point. Okay, and as you continue to move along the x-axis for any value you can find along the x-axis, is there anywhere during that graph that you find more than one point to go along with each x? Okay, So anywhere I look, for each x I find, I only find one y. Okay, so to come back to their question, is this a function that we're talking about in this problem? Yes, it is. Because any x that you can find in the problem or in the chart or in the equation or in the mapping or anything else they give you, for each x, there's only one y. Okay. All right. So yes, it is a function. It says explain why or why not. Well, guys, the explanation is simply the restatement of the definition. Yes, it is a function. Why is it a function? Because for each x value, there is only one y value that goes with it. That's the explanation. Okay, and I want you to keep that explanation very simple and very focused in your mind, because it doesn't matter. Graphs, equations, charts, mappings, anything that they give you, this definition will apply to all of it. Okay, so for each x, there can be only one y if it's going to be a function. Okay, all right, we'll pick it up with the remainder of the questions on this tomorrow, so please bring this packet back with you. We'll work through the rest tomorrow and go from there.